So let's continue. Last time we talked about this normalization of Coulomb interactions in this electron gas, and those electrons are interacting with one another by Coulomb interaction. And we know that this Coulomb interaction not only renormalizes the self-energy or electron energy, but also it modifies the Coulomb interaction itself. So the reason why we have such a vortex correction, this is called vortex correction, which modified this dashed line representing this Coulomb interaction. And the reason why we have such a vortex correction is precisely because of the Coulomb interactions itself, and this Coulomb term could be expanded to higher orders. So the lowest non-trivial order that you could Taylor expand this Coulomb interaction in this effective action or this partition function is the second order term, right? So this two solid line represents the initial state, and the two outgoing propagators are the outgoing or final states. Okay, so two in and two out. So that's Coulomb interaction. So the Coulomb interaction bring together this two electrons that get scattered by the Coulomb, and then they are scattered out. So you could imagine that you could have such a higher order or second order term in this Coulomb potential U. So this is the bare interaction where you only have this very trivial or simple U0 interaction, which is the Fourier transform of this Coulomb, one of our potential in three-dimensional space. But you can imagine that I can have such a second order term. But we have discussed this weak contraction theorem, right? So when you are dealing with this perturbative expansion of your interaction, so you could connect all these internal propagators of electrons and form a loop. In other words, you could do this to actually give you some non-trivial contributions when you evaluate this expected value of C dagger C or psi dagger psi, but in a perturbative way. So you could connect all these intermediate propagators in between these two dashed lines. And this is precisely what we call this vortex correction, because this kind of a bubble in the middle renormalizes this dashed line, because you could consider this as some kind of a black box which I enclose by these orange lines. So this stuff or diagrams inside the orange box is actually precisely the same as that box right here, which is actually normalizes the vortex point, which is the intersection point among this dashed line and this two solid line there. So this should be understood as some kind of correction to this three-leg interaction point right here, and this is called vortex point. And this diagram, this bubble in the middle, actually normalizes this three-leg diagram, one dashed line and two solid lines. So we call this vortex correction, and it is the vortex correction that will lead to many interesting quantum phenomena, such as the screening of a Coulomb potential and also the dielectric function. But we need to sum over all such kind of a bubble diagrams inserted in this interaction propagator, and this is the diagrammatic representation of such an infinite number of diagrams. So this shaded box represents the renormalized Coulomb potential, and you could consider this as a summation over all these vortex correction diagrams, including the bare one, which you don't have anything, and you could consider this empty box as just a dashed line, okay, representing just a bare this Coulomb propagator, which you know that this is simply just a photon. But you could have additional contributions coming from this bubble in the middle of this dashed line, and this is represented by this kind of a cartoon picture. So you could consider this as just some kind of dashed line, but you have some kind of propagator in the middle, and then another fully dressed vortex. So this shaded yellow box or orange box represents, again, an infinite number of bubble diagrams that you could insert in between these two dashed lines. Okay, So to represent such an infinite number of bubble diagrams, we could re-express or replot this kind of a vortex correction diagrams in this manner, so that this wavy line represents renormalized Coulomb interactions, which includes all the contributions, including the bare one, the simple dashed line, and one bubble inserted in the middle of this dashed line, and also two bubbles, and three bubbles, and four bubbles, an infinite number of bubbles. And you could organize all these bubble diagrams inserted in the middle to actually look like this diagram. So let's just do the algebra. So you could, in some textbooks, you could use this wavy line or a double wavy line for this renormalized Coulomb interaction. So let's just consider this as just a single wavy line denoting the renormalized Coulomb term, which is given by U0, which is the bare Coulomb interactions, plus the single bubble. The single bubble diagram consists of this U0 over here and a bubble diagram, which I call this pi 0, q, and omega. And we will calculate this bubble diagram later, but this is just a symbolic representation of this so-called electron hole pair bubble diagram. And of course, we have another U0 over here. So that's what I wrote here, U0, pi 0, and U0. And for two bubble diagrams, you could follow the same rules, that you write U0 on top, and then pi 0, and then U0, and pi 0, and U0. And so on and so forth. You could just imagine you have infinite number of such a bubble diagrams in the middle. And so let's just reorganize all these terms in a slightly different notation. So in some textbooks, you represent such a renormalized Coulomb term as a double wavy line. A single wavy line is just a bare Coulomb propagator, and then this is a single bubble diagram, and two bubble diagram, and three bubble diagram, and so on and so forth. So you could really rewrite the remaining part of the bubble diagrams by pulling this common factor, this single bubble in front, and then multiply by all these diagrams in the bracket. But in the diagram, the first term will be just a bare Coulomb propagator, U0, and the second term will be a single bubble, and so on and so forth. So you simply just take away the single bubble and put it in front and multiply by all the other remaining parts. And you will see that this diagram inside the bracket represents precisely this full Coulomb propagator, because this is also an infinite number of diagrams. So starting from this no bubble, single bubble, and two bubble, and three bubble, and so on and so forth. So the diagrams inside the bracket represents, again, the renormalized Coulomb propagator, which is double wavy line. So you have two double wavy lines, one on the left-hand side of the equation, another on the right-hand side of the equation. And this diagram represents precisely the diagram that I just plotted earlier, that you have a single bubble attached to this dashed line, but then this single bubble connects to this fully dressed, fully normalized Coulomb vortex, which is the same type of a shaded box appearing on the left-hand side of the equation. So this is the kind of a shorthand notation for this so-called this RPA, random phase approximation. Or in some textbooks, this is called the ring diagram, because the diagram itself, the single ring, the two rings, looks like the wedding ring. The wedding rings, you could have this single wedding ring or two rings and three rings. And when you sum over all the ring diagrams, and you could actually call this fully dressed renormalized Coulomb term. Of course, this is not the full diagram. You can imagine you could have all different types of diagrams other than the ring diagram. So some more complicated diagrams, okay, which we neglected here. But in many, say, Coulomb interacting electron gas system, this corresponds to many metal compounds, and this RPA is good enough. So when you sum over all this ring diagram, you get this Dyson type of summation, which we have discussed already. So this is U0 divided by 1 minus u0 pi 0. So this is the way that we estimate this, the renormalized Coulomb interaction coming from the vortex correction. And next step is to calculate the single bubble, which we call this pi star or pi 0 inserted here, and we could apply these Feynman rules in momentum space and to integrate over this internal degrees of freedom and to get this q and omega dependence of this single bubble. Okay? Sometimes in some textbooks they call this vacuum polarization, and as we'll see in just a moment that this vacuum polarization bubble is nothing but the density-density correlation function. So this pi 0 is in some sense proportional to the correlation function between electron density operator at different space and time, meaning this electron can actually get polarized into this electron hole bubble, and then this electron hole bubble will recombine at some point, and this bubble vanishes. So in other words, out of a vacuum, this photon can actually splits into electron hole pair kind of excitations, and those electron hole pair excitations are simply just some kind of intermediate virtual states, and this virtual state will decay, and they will decay into another photon. The photon decay into electron hole pair, but this electron hole pair will not live forever, and they decay into a photon. Again, this photon mediates this electron-electron interaction. But this kind of vacuum polarization happens just automatically by quantum mechanics. So this would not arise if you consider a classical electron gas. So the classical system, you would not have such kind of vacuum polarization, and we will see later that this consequence of this pi 0 in the static and long wavelength limit corresponds to the Thomas Fermi approximation that you learned previously to account for the screening of electron gas, and which is a semi-classical treatment of electron screening effect. But in more general case where both q and omega are non-zero, and you cannot make progress without using Green's function method. Okay, so this is a purely quantum mechanical problem at finite temperature and finite momentum and finite frequency. But this vacuum polarization can be observed experimentally at low temperatures in many Coulomb interacting electron gas. So this effect is real, and we should study this effect. Any questions?
Excuse me,
Yeah.
I have some question. Because you here you use a single wavelength line for the renormalized interaction, right?
Right.
But I think that is the same as double wavelength, because the right hand side you
Yeah, so I apologize for this kind of a different notation. So if you like, this is the double wavy line, and this will be a single wavy line, if you like.
No, I just think the first one, because that single and double totally different.
Right. So I think I could just unify this notation like this. There's no dash line, just a single double wavy line. But if you look at different textbooks, they have different conventions. In some textbooks, this renormalized Coulomb term is represented by this double wavy line, but in some textbooks, it's just single wavy line and a dash line, okay? Or a double wavy line or a single wavy line. So it depends on your convention. So it doesn't matter as long as you know the precise definition, okay?
And another question for this diagram, Vertex correction, and you have a two boxes and connect by the Green's function, but why
Right.
not G0 but G?
G0.
Yes, I mean the two boxes. There's a two boxes, right, for the Vertex correction.
Right. So this is, maybe this is another convention. So this is G0. Okay. Okay, so if not, let's take a break, and when we come back, we will study this pi 0 diagram. Okay, so let's just continue writing down this equivalent expressions for this vacuum polarization. And so as we defined already, this is double wavy line stands for this effective Coulomb potential term in Q and omega space, and which is given by a single wave line, which is the Bayer propagator, U0 plus a double shaded vacuum polarization bubble, which represents the sum of all these bubble diagrams. So you could just expand this double shaded polarization bubble, which we call this pi, in terms of this single shaded pi star, or we call this proper polarization bubble. Okay, so you inserted the 1 pi star and 2 pi stars and 3 and so on. And so when you sum of all such a pi star bubble, and you get the full corrections to U effective, and this is given by U0 divided by 1 minus U0 times pi star. So as I mentioned already, this pi star is the key. So, but you could also rewrite this relation between this pi and pi star as the pi is the full polarization bubble, which is made of a single bubble plus this 2 bubble and so on and so forth. So when you sum over all such a single bubble connected diagrams, you get this pi. So pi is related to the pi star by this formula, and so you got 2 equivalent expressions. One is starting from this U0, and you sum of all these diagrams, including this infinite number of these terms of this pi star bubble. And another way to look at this is that you just calculate this effective polarization bubble, which is again an infinite number of Dyson type summation of the single bubble pi star diagram. So as I mentioned, this random phase approximation is approximation that we simply just take the lowest order approximation to pi star. So in general, pi star can have higher order contributions other than this single bubble. But you could imagine that at higher orders, this pi star could have a more complicated diagrams than it's just a single bubble. But the single bubble is the lowest order term that you could get to actually serve as a pi star. Okay, so in that regard, this is called a random phase approximation. So we single out just a bubble, this particle hole bubble, as the lowest order approximation to this pi star, and then we only take into account such bubble diagrams. So now with that expressions, we can define these dielectric functions. As I mentioned previously, this inverse of epsilon, which is a dielectric function, is defined as the ratio of this U effective, the full renormalized Coulomb term, divided by this Bayer Coulomb interaction strength U0. So U divided by U0 defines inverse of epsilon. So now you could just use that Dyson type of relation to show that this 1 over epsilon minus 1 is given by U0 times pi. And remember, pi is given by this kind of a geometric sum of pi star. And then you could rewrite this equation and to get this second line, which is say that epsilon is given by 1 minus is U0 times pi star. So these two lines are really straightforward consequences of these two. Okay, so I assigned these derivations to you as a homework exercise. It's just a one-line proof. Okay, so next step is to really calculate this bubble diagram and to link this bubble to this density-density correlation functions I mentioned. So we don't have time to proceed, but we will do it tomorrow. So next is that this epsilon, so 1 over epsilon minus 1, which we define this as some kind of a charge susceptibility, chi, and this chi is actually proportional to, or is defined by this real part of the density-density correlation function. Capital D retarded as function of Q and omega, and this capital D retarded is some kind of density-density correlation. So the static limit, this is the capital D as function of Q, and omega goes 0, is nothing but this correlation functions of electron density. Okay, so this N of Q represents this electron density operators. Okay, so we will see next time that epsilon, or dielectric function of solids, is related to this density-density correlation function. Okay, so what is the density of electron? Of course, this is our rho of Q, right? Okay, so we will make such a connection, okay, next time. So to summarize this, so we just learned that this Coulomb interacting electron gas shows some of this non-trivial vortex corrections which come from this electron hole bubble, and based on this vortex correction we can define this dielectric function which is responsible for the screening of a Coulomb potential, and you'll see that this is precisely this dielectric constant that we familiar with in the static limit and the long wavelength limit. Okay, when both Q and omega go 0, this epsilon is precisely this dielectric constant that we are familiar with. So in metals, because of this screening effect or because of the vortex corrections, this epsilon plays a role as a screening of a Coulomb long range force. So this epsilon, the presence of epsilon, really cut off this long range tail of this Coulomb potential, and the consequence of that cut off this long range Coulomb force is that this electron's field actually kind of a short range Coulomb repulsion, okay, because of all these electron hole bubbles that can be created instantaneously by quantum fluctuations, and so that will lead to the screening of Coulomb potential, and we will come to that point tomorrow. Okay, so I guess that should be enough for today.
Excuse me, Professor. If we in RPA you take the lowest order like the G0, right?
Right.
My question is, according to your experiments, for the finite temperature, how much effect for the dielectric function? The temperature dependence dielectric function.
We will see that as well in the following. Okay, so of course that's definitely showed very important role. So in high temperature limits, this epsilon behaves as just classical, say Thomas Fermi dielectric function. But in low temperature regime, you got new features. Okay, so we will see that in a moment because this connects to the fact that this excitations of this particle hole pairs should intersect with the Fermi sphere. There are two Fermi spheres play a role here because we have two operators, right? When we evaluate this and correlator, it involves, say, two Fermi functions in general, okay? So in high temperature limits, you don't see much of a difference between classical, semi-classical treatment, but in low temperature regime, because of these two Fermi functions, can or cannot overlap, okay? In general, may or may not overlap. It will give you very different contributions at low temperatures.
And another question, in the RPA, can I say that this approximation is more suitable for the system that more easy have an electron hole pair? But how about if the system not easy have an electron hole pair? For example, for a molecular, we will not use an electron hole as language. Is it always in a semiconductor, right?
Of course, this kind of a formulation is appropriate for describing, say, metals mostly. Okay, for a semiconductor, you may have a different type of excitation, such as exciton. Okay, and suppose that you should replace this particle hole pair by some other diagrams in different systems, but the general principle is the same. Okay, so you look for this lowest order contributions to the Bayer propagator of your interaction strength. Okay, and this interaction may not be Coulomb, but in most cases in solid state they are Coulomb for sure. Okay, and this may describe some part of the insulators as well. This Coulomb interactions also affect some insulator. But of course, for magnetic materials, this may not be sufficient. Okay, you may take into account other effects such as the spin-spin coupling. But we are just studying a very simple system that mostly metals or Fermi liquid, okay, ordinary metals. But even so, this is highly non-trivial. All right? Okay, good. So I'll see you tomorrow then.